All right, here we are, the last part of 3-2 today. I still haven't gotten a negative COVID test, so I'm try one more time today. So pray for that. I need to come back tomorrow because I want to do 3-3 with you guys. So here's the end of 3-2. Hope the quiz went okay. I let you use your notes, which I've never done before, but you know, I have some major teacher guilt this week of staying home. Okay. All right. So correlation and regression wisdom. We got to have some wisdom when doing these problems. So which of the following, look at these four graphs, has the highest correlation? Well, it looks like this is pretty linear here, and this definitely shows a parabolic shape. This one has a line with a weirdo up here that has a high residual, and this one, I don't know what's going on with that over there. It's crazy. So I bet that would probably be more like that because it's going to pull this one that way. And this one's going to be pulled that way. Oh, okay, it looks like he's got a pitchfork. Okay, anyways, so this is a trick question, actually. Trick question. All four graphs have the exact same correlation. They all have a correlation of 0.816. Okay, and not only that, it's really interesting. It's really interesting. They all have the same least squares regression line equation too. And this is what it looks like, 0.5x. So I should have drawn the exact same line every single time because they all have the same line. So the moral of the story here, the wisdom that you need to get from this is you always have to graph your data. Graph your data, okay? Look at the scatter plot. See what it is. See if it's linear. This is obviously not linear, and I'm given this pretty high correlation, but I can only use R when it's linear. So graph your data. On the quiz, I didn't give you a graph of the data, but I did give you a graph of the residual plot, which is also good to have too. Okay, so here we go. Points can affect the correlation R, the equation of the least squares regression line, the coefficient of determination R squared, and the standard deviation of the residuals. So there are three cases in each scatter plot. The 8 points closest to 0, 0 are the same, and based on the additional 9th point where that's located, okay? So here's the original data, and we're given a y hat, R is 0.49, R squared, and then the standard deviation of the residuals. So what do you notice with each case? So in case number 1, they decided to add this point out here. Now they added a point on the line, okay, very far away, X and Y from the regular points. So what do you notice changed from these things? Well, obviously the least squared regression line stayed the same. Okay, so we're supposed to discuss slope, intercept, correlation. So the slope and the intercept both stayed the same because the point that was added was on the line. So it didn't change it. It didn't pull it any direction. Okay, now take a look what happened to R. Wow, what a big difference. 0.49 to 0.96, R squared. So R and R squared got stronger. Okay, a better correlation happened because of that 1 point that was added way out there. And then also the standard deviation, S, went down, it shrunk, okay? Because this one, adding this point on the line adds a residual of 0. And then when you're adding those up, it actually helps the standard deviation go down. Okay, let's take a look at case 2. Case 2, they added this point. This point, there's a big change in X, but there's no change in Y, okay? And so what happens is, your line's gonna change a lot from, okay, we're always comparing it to this original right here. And so what happened to the slope? Well, the slope went from 2.51 to, no, sorry, I was looking at the wrong number, 0.80 to negative 0.52. So the slope changed, and the slope changed actually from a positive to a negative. So the slope changed a lot. You don't even have to say that it changed from a positive to a negative. It changed a lot. We kind of think of this as this line right here. By adding that point right there, it pulls the line down, and you think of this as a teeter-totter. Okay, so the slope gets changed like this direction, and then the y-intercept actually goes up. So think of it as the whole line is changing like a teeter-totter, and it affects both the slope and the y-intercept. And so the y-intercept went up because that line was getting pulled down. So then the rest of the line would go up. So the y-intercept went up. It increased a lot. Let's take a look. R went from, when we're comparing it from here, 0.49 to negative 0.32. So R got weaker. Not just because it's negative, but it's 0.49 and negative 0.32. That's not close to -1. And R squared got really weaker too. So R and R squared, they both got weaker. And then what about the standard deviation? Or the standard deviation of the residuals went up a little bit. So S went up a little, because the reason why it only went up a little bit is because there was the change in X, not the change in Y. Y is the change from actual to predicted. That's going to be the residual there. So in this case, X didn't, or X changed a lot, but Y didn't. Okay, and let's look at case 3. So they've added this point right here. And if you take a look, I've got a lot of stuff on here. Let me see if I can erase some of this. I guess not. It's not letting me do anything. Ah, there we go. Okay. Sorry, I don't like all this stuff on here. So we're still comparing it to the original. And if you take a look, let's take a look at the least squares regression line. Okay, the slope stayed the same. The y-intercept went up a little bit. So basically this line that was right here, it basically just shifted up, like they're parallel. Parallel lines have the same slope. Okay, and so the slope stayed the same. And this is a big change in y from the rest of your points. Okay, it's not a change in x. There's still the same x values in here, but it's just a change in y. The y-intercept went up. So the line got pulled up towards that weird point up there. R got weaker, 0.11. R squared is really weak. So R and R squared got a lot weaker. But look what happened. I wrote leaker. Oh, weaker. I'm pretty weak. To the standard deviation. The standard deviation is what got affected the most here. So S changed a lot. It changed a lot because that's a huge residual. If you have this point right here, and you look at the residual and you do the sum of the squares of the residuals, that's going to add a lot to the standard deviation. And so the standard deviation changed a lot. Not only did it change a lot, it went up a lot. It went up a lot, okay? So all 3 of these points, this one was a big change in X and Y, but it was in the line. This one was just a change of X, not a change of Y. And this one was a change of Y. And we're going to talk about what these points are called in a little bit. Something to look forward to. All right, let's go here. All right, this one is an influential point. This point right here. Sorry, let me see. This point right there, that's an influential point. And the reason why it's influential, it didn't change the least squares regression. It didn't really change the standard deviation, but it changed R and R squared a lot. Okay, all of these are influential. All 3 of these points are influential. Now they're not all outliers, which is very strange. You'd think that this one would be an outlier. But if you go going back and forth here, the only one that's an outlier is case 3. That's going to be an outlier because it's going to have a large residual because it changed the standard deviation a lot. This one didn't change much, 3.0 to 4.27. This one's really not considered an outlier because, I mean, it is away from the points, but it has to also have a large residual. This is a high leverage point. Next page. Okay, here we go. So there's a couple of definitions here, and these get a little tricky. I'm going to warn you. Okay, so points with high leverage in a regression have a much larger or much smaller X values than the other points. So it's not about the Y at all here. So high leverage goes with X, okay? An outlier in the regression is a point that does not follow the pattern of the data as and has a large residual. Okay, so an outlier does not follow the pattern, but the word and has a large residual, okay? So it has to be both of those things to be considered an outlier. Now, all the points on the last page, they're all influential, because an influential point, if removed, substantially changes any of these things. If you add a point and it changes the slope, or the y-intercept, or r squared, or the standard deviation of the residuals. Okay, if it changes any of those things in any way, it's influential. Okay, so if we go back to these other points, a definition of what an outlier is, it doesn't follow the pattern of the data and has a large residual. Okay, so remember high leverage? The x values are very different than the other data. Okay, so those are kind of hard words to get straight. You think, oh, they're all outliers. They're all weird. They're all different points. Okay, but remember, go back to the definition. If it ever says, which one's an outlier? It does not follow the pattern and has a large residual. That's from the book, okay? Okay, outliers and high leverage points are often influential. Okay, so most of them are going to be, if it's changing anything, it's influential. It's influencing the graph. Now, to calculate the equation of the least squares regression line using summary statistics. Okay, this is going to be the slope is equal to r times the standard deviation of y over the standard deviation of x. This is on your formula sheet. Okay? And then also this is on your formula sheet too. The least squares regression line passes through the point x bar, y bar. So you can write y bar equals a plus b x bar. That point, x bar, y bar, that's the average of all the x's and the average of all the y's. That point will always be on the least squares regression line. Okay, so let's talk about influential points in the pattern and out of the pattern. So if you have an influential point in the pattern, R is going to get stronger, much stronger actually. We saw that in the last problem. The least squares regression line won't change much. Okay, won't change, and S won't change much either. Okay, so this is kind of just summarizing all the stuff that we did on that last page. Now, an influential point outside of the pattern is going to make R weaker. Okay, it's going to change the least squares regression line a lot, sometimes a lot. Okay, and S will increase. If y has a big change, but not x. S won't increase if x is the point that's changed. Okay, so let's look at an example. Here we go. The scatter plot shows the payroll of millions of dollars and number of wins for Major League Baseball teams in 2016, along with the least squared regression line. The points highlighted in red represent the Los Angeles Dodgers from the far right, so that's LA, and the Cleveland Indians. So this is, I don't think they're called the Indians anymore. I don't know. Things got weird. Okay, describe what influence the point representing the Los Angeles Dodgers has on the equation of the least squares regression line. Excuse me. Well, since this point is further out this way, okay, and if you were to picture taking that point out completely, what would happen to the least squares regression line? It would probably go like that, because this point is kind of pulling it down towards it. And so we can say, hold on a second. We can say that since LA is on the far right, and below the least squares regression line, it will decrease the slope, okay? It will decrease the slope. So that point, it pulls the slope down this way. But remember, think of this as a teeter-totter, and when that point gets pulled down, what happens is it will increase the y-intercept. Okay? So that's what that point is doing to that least squares regression line. Now describe what influence the point representing the Cleveland Indians has on the standard deviation of the residuals and R squared. So that point has a pretty large residual, okay? And so that point, the Cleveland Indians, because it has a high residual, it makes the standard deviation, it makes S larger, and it will make R squared weaker. Okay, it brings down R squared, the percentage of variation that's explained by the line. Okay, so that's what those couple of points do. They could have talked about that point or maybe even that point, but they just took 2 points off of there and said, how is this affecting our line? How is it affecting the standard deviation? Okay, now suppose the scatter plot below on the left has R equals negative 0.82. What would adding the circled point scatter plot on the right do to the value of R? Okay, so it looks like it's fairly linear. And if you draw this, what happens is it ends up being in the pattern. It's in the pattern of our line. Okay, and if you go back up to here, what happens when it's in the pattern with R gets stronger. So this would, now I put this on a quiz one year and I tricked some people on accident. I don't try to trick people, but they said that R will increase. If R increases, that means it gets further away from -1. You don't want to say that. So it's in the pattern, so R will get stronger, okay? Or you could say it will get closer to -1. Closer to -1. But that doesn't mean that it gets bigger or doesn't, yeah, like negative 0.82 gets, larger that or higher or something. Yeah, you don't want to say that. You want to say it gets stronger or that it gets closer to -1. Okay, real quick before we move on to the next page. This graph up here, I'm going to erase. Okay, no, I'm not going to erase. Let me see. Gosh, I hate Notability. Or no, I love Notability. It's not Notability that I'm in. It's trying to get rid of this. There we go. I'm in Explain Everything. I'm trying to explain everything to you guys. Okay, so if you look at this graph right here, I'm going to tell you that the average of all the X's. So if you took all the payroll in millions of dollars and you took the average of that X bar, the average is going to be 150 in millions of dollars. And then if you took the number of wins and you averaged those, you found all the number of wins and you averaged them out, and that was going to be about 80. It was 80. Okay, now if you add those lines, those equations, okay, like X equals 150, that's a vertical line. Okay, that's the line of X bar. And if you add Y bar equals 80, that would be a horizontal line right here. You will see that that point right there is the point X bar, Y bar. And it will always be on the least squares regression line, always. Excuse me. So if you ever needed a point on this graph, we don't know what the Y hat is, but we do know that the point 150, 80 is on the equation of that line. So just so you know, we're going to probably have a problem with that coming up pretty soon. And there it is. Okay, here we go. This is using your summary statistics. That's what it's called. This is when we would go to the formula sheet and I would let you you get the formula sheet no matter what. So it says we collected data from a random sample of 15 high school students to investigate the relationship between foot length and height. Excuse me. Almost to my maximum capacity of words today. The mean and standard deviation of the foot lengths are X bar and SX, and the mean and standard deviation of the heights are Y bar and S sub Y. The correlation is, okay, find the equation of the least squares regression line for predicting height from foot length. All right, so on your formula sheet, you are given b is equal to r s sub y over s sub x. I'm gonna pause this real quick. Okay, whew, I got some cough medicine and all right. And this is just an algebra problem. I know it doesn't look like it, but it actually is just a slope-intercept problem or point-slope form or whatever you want to do. You do have to know, this formula though in order to do this. Okay, so our job is to find the least squares regression line. So y hat equals a plus bx. We need to find a and we need to find b. Well, b is the easier one to find. B is found by using this formula. Okay, anytime you're given this information and y hat, you know that you're going to use this formula. That's the only time you ever use this formula is when you're given that information. So let's go ahead and find the slope. So we have r is given to us as 0.697. Sy is 10.69 divided by 2.71. Okay, and beep boop beep boop, use your calculator, you get 2.75. Okay, so I have the slope. I can go ahead and put that in. A plus 2.75x. All right, now also on your formula sheet is this formula. Y hat equals a plus b x, or sorry, not y bar equals a plus b x bar. Okay, and so you can do this one of two ways. If you are, you know point slope and you want to use that, go ahead. The book teaches it this way, like you have no idea what a line is or how to find the equation of a line, which I know all of you do. So we're going to go ahead and put y bar in. So 171.43 equals a plus 2.75 times x bar, 24.76. All right, and then you go ahead and multiply, subtract to the other side, solve. A equals 103.34. All right, so we are ready now to write the equation of our least squares regression line. So y hat equals 103.34 plus 2.75b. Nope, not b, x. Okay, where y hat is the predicted height. Okay, predicted height, and x is the foot length. Don't forget to do that. I did remind you on the quiz. I hope you remembered to label your variables or identify your variables. Okay, last question. We're almost there. Here we go. We got Shaq coming up. See, can't be bad. All right, describe the hypothetical scatter plot of heights and weights of high school students, ignoring the three labeled ones. So we're going to ignore Kasugao and Shaq and Manute Bowl. Okay, we're going to ignore them. Describe the hypothetical scatter plot. Okay, describe. We're talking about Duffs again. All right. So we would say the relationship between height and weight of high school students is, okay, so let's come over here and look. It looks positive, fairly strong, with no unusual points, because we're ignoring the three weirdos, or I shouldn't call them weirdos. Fairly strong with no unusual points. All right, so hopefully you did that on the quiz today. Yes. All right, now consider each of these men one at a time. Identify whether any of them are likely an outlier, high leverage, and or influential. Okay, so don't forget, an outlier has a high residual and does not follow the pattern. Okay, high leverage has a big change in X, and influential will change anything on the graph. So all three of those are going to be influential for sure. Okay, so let's take a look at Shaq. Shaq is 7'1" and he weighs 325. Okay, so 7'1", 325, there he is, but he is in the pattern of this line that I drew. Okay, so I would not call him an outlier. He is far away on the Y's, on the X's from everybody and on the Y's, okay? So I would say that Shaq is a high leverage point. High leverage point. Okay, oops, point. Because the X, you know, he's further down the X's than the rest of them. We're ignoring Manute. It's just like the high school kids and then Shaq. Okay. He's high leverage and influential. And the reason why he's influential is because he will increase, his data point will increase R and R squared. It won't change the equation of the line at all. Maybe the standard deviation will go down a little bit, but it's going to make R and R squared stronger, and so he has some influence on the data from the line. Okay, let's look at the sumo wrestler. He's 6 foot and weighs 340. He's way up here. Let's get rid of Shaq now. We don't care about you, Shaq. I'm sorry. How come I can't erase sometimes? It's so annoying. Okay, so the sumo wrestler, he has a very high residual to this line that I drew. Okay, and anytime you have a high residual, this would be an outlier. And because he has a high residual, this is going to increase R. No, I'm sorry. It's going to increase S. It's going to make R weaker. It's going to increase our standard deviation, and it's going to make R and R squared go down. So he's an outlier, and his data point is also I was doing so good, you guys. Influential. Okay, and then finally, Manute Bol. Here's Manute Bol. Let's see. Manute Bol is going to change this. It's going to bring down the equation of this line. Okay, so that it would be more like this, which means he's not going to have that high of a residual because it is going to get pulled down towards it. Okay, so, but he does have a very different X than the rest of them. The X's stop here and he's way over here. So I would call that data point high leverage. I wouldn't call it an outlier though. I know it's so weird. The Y's are going to be the outliers. But Manute Bol's point is also influential because it's going to change, the least squares regression line will change a lot. Okay, the slope is going to come down and the y-intercept is going to go up. And so that's how that would change. So all three of them were influential. Okay, sumo wrestler was outlier and the other two were high leverage points. All right, if you go to the next page, okay, so you can see that those definitions are here. And then we will start 3.3 on Friday. I hopefully will be there, okay? Thanks for listening in. I'll see you guys. I miss you. Bye.